Okay, good morning everybody, and welcome to our first class of calculus. The full name of the course is Differential and Integral Calculus. But we're going to just call it Calculus for short, or Calculus 1, right? There's another course called Calculus 2. And what I want to do is start by diving right into the deep water and presenting a few theorems. Okay? So, a theorem is a fact, a mathematical fact, that one needs to prove. Okay? And we're going to learn over the course of the course many theorems and how we prove them. And right now I'm going to write our first theorem for this semester. And some theorems are really attributed to specific famous mathematicians, like this one, which is by Fermat. So Fermat was a French mathematician. He's very famous for a different theorem than the one I'm going to write now, called Fermat's last theorem. Maybe you've heard of it. But that's not the theorem I'm going to write. So this theorem says the following. Let f, I'm going to write the theorem and then we're going to go word by word and explain and verify that everybody understands everything. Let f be defined in AB, and let x0 be a maximum point or minimum at which f is differentiable. Then f prime at x0 equals 0. Okay, so theorems also have this form. They start with some assumptions, some data, some setting, okay? Maybe they would start with the word let or the word suppose or something like that. And after setting up the framework for the theorem, there's going to be a then, which is what the theorem asserts, okay? And what we need to prove is the then part. Okay? So let's understand what this theorem says. Okay, so what's f? A function, right. Has everybody encountered functions? Some form or another? Okay, so you know what functions are, right? They have graphs, right? Everybody knows that? Okay. So we're going to be discussing functions a lot, and we're going to start from the very basics, but this is just the introduction. So let f be a function, and I'm assuming that it's defined in AB with these roundish parentheses, okay? This is called an open interval, okay? So what this denotes is, suppose this is the x-axis, this denotes, let's give an example. For example, from 2 to 5, this denotes the interval of all the points between 2 and 5. Okay, let me bold it in blue. So this is the interval 2, 5, not including the endpoints. Okay, so when I write like this, it means that 2 itself and 5 itself are not blue. They're not included. Okay, this is called an open interval. So I'm assuming f is defined on some open interval like this, AB. And let x0, so this is just some point in the interval, be a maximum point or minimum, so the theorem works for both, a maximum point or minimum. So what's a maximum point? Let's do another drawing here, maybe down here. So here's the x-axis, and here's the y-axis. And let's say this is the point A, and this is the point B. Okay, so this is the interval on which f is defined. And f has some graph. Okay, so I'm going to draw some graph, maybe something like this. So this is the graph of f. And a maximum is a point where the function gets its biggest value. So in this picture, for example, this is the point x0 where the function has a maximum. Okay? And formalizing this, so a maximum, maybe I'll write it like this. So a maximum is a point, saying that x0 is a maximum means that the value of f at x0 is greater than or equal to the value of f at x for any, do you know this symbol? This symbol means for any. It's like an upside down A. Okay? For any x which belongs to, do you know this symbol? Okay, so this is kind of like the symbol of the euro currency. Okay? Belongs to the interval, the open interval AB. This is what it means for x0 to be a maximum. Okay? Now, what we're going to be doing throughout this semester is we're going to be learning, one of the things we're going to be doing is we're going to be learning a new language. Okay? We're going to be learning more rigorous math. Okay? So a language comes with words, comes with an alphabet, with letters, with symbols, and we're going to communicate gradually through that language. So whenever you see a symbol which you haven't encountered before, ask what it means. Okay? Okay, so this is what it means to be a maximum, and here's the drawing that you should have in mind. Okay, so a maximum at which f is differentiable. Now this word, as I mentioned earlier, is one of the words in the title of this course, right? Differentiable and integral calculus. That's the full name of the course. And we're going to discuss this word a lot. A lot. But for now, I'm just going to give you a bit of intuition, what this word means. For a function to be differentiable, what it means, what you should have in mind intuitively, is that the graph of the function doesn't have any cusps. Okay, no sharp points like this. Instead, it's smooth. Okay? Is that clear? Okay, no pointy things. So, for example, this picture that I drew here is nice and smooth. No points, no cusps. Okay? So that's the intuitive meaning of differentiable. So all these are, this is the setup, this is the description of the assumptions of the theorem. And then there's the conclusion. The conclusion, f prime, do you know what f prime is? What's f prime? The derivative, right? So the derivative of f at x0 is 0. We're going to discuss derivatives a lot. That's directly related to this word differentiable, right? But how do you intuitively think of a derivative? Right, the slope of the tangent line. So saying that the derivative at this point is 0, intuitively is a way of saying that the slope of the tangent line at this point is 0, meaning that the line is horizontal, right? So the slope of the tangent line at the point x0 is 0. Okay? So do you agree that this picture really reflects what this theorem says. And it's kind of convincing, right? If you think of a function which is smooth, no cusps, and you look at a maximum point or a minimum point, the slope of the tangent line there is going to be 0. Does everybody vision that? Can you see that? Can you see this theorem? Okay. Everything we said so far is just intuition. It's not a proof. We're going to get to proofs. But intuition is another important part in learning math. Okay. So do you see that this is the intuition for the theorem? Okay, good. Now, okay. So let's put on our second theorem. And this second theorem is named after another French mathematician called Rolle. I don't know if there's anybody French here, but you can tell me how to pronounce it. Rolle, right? Is that correct? Okay. Rolle. Okay, and it says the following. Let f be continuous on AB. Again, I'm going to write everything and then explain. And differentiable on AB such that f at A equals f at B. So these are the assumptions. Then there exists a point C in the interval AB such that, this is short for such that, the derivative of f at C is 0. So let's read this theorem, okay, and see if we understand it. Okay, so we're assuming f to be continuous. Continuous is another word we're going to discuss heavily later on. And again, I'm just going to give you intuition, which you probably already know. A continuous function, intuitively, is a function which you can draw without lifting the pen off the paper or the marker off the board. Okay? So it doesn't have any jumps like this. Okay? It's continuous. Is that intuition clear? Do you all know that intuition? Okay. So we're assuming it's continuous on AB. Note that this is a bit different than this. Here we have these square brackets here. Do you see that? So what this means is a closed interval. It's almost exactly the same as this open interval, except that now it includes the endpoints. Okay? So, for example, the closed interval between 2 and 5 is all the numbers greater than or equal to 2 and less than or equal to 5. Okay? Question?
Yes. Does it necessarily mean that A and B are not differentiable?
No. Okay, wait. So the question was, does it necessarily mean that the function is not differentiable at the endpoints? Okay, wait. We're going to discuss these definitions, what it means to be differentiable, the formal definition, not just the intuition of being smooth, but the formal definition later. Okay? And then we're going to be able to say correctly what it means to be differentiable at an endpoint. Okay? And then we're going to see this theorem again. We're going to see all these theorems again. But after we've already learned formally and accurately all this terminology and all these notations and definitions, and then we're going to be able to answer good, delicate questions like that. Okay? For now, this is just an introduction. Okay? So I'm really being a bit vague on purpose. Okay? Just an introduction. there's going to be a point to this. Okay? So we're assuming it's, if you want, you can just think continuous and differentiable on the interval. That's really what matters. So what you should have in mind is a function that is smooth, right? No cusps, because it's differentiable, and no jumps, because you can draw it without lifting the pen off the board. Okay? And another assumption is that the values at the endpoints are the same. So the picture to go along with this drawing will be something like this. If this is the point A and this is the point B, the value of the function at A, here it is, some value, has to be the same as the value of the function at B. Right? That's this assumption. And now the function is nice and smooth. Okay, so I have to be able to somehow draw it to get from here to here smoothly without lifting the pen off the board. Right? And what the function says is that there's going to be some point C in the interval. This means belongs to, right? We've seen this symbol already. Such that the derivative at C is 0. So let me convince you intuitively that this theorem also makes sense. Okay? Well, if the function is just what's called a constant function, then the derivative at any point is 0. Do you agree? Okay, so that's the boring case. If it's not a constant function, then, well, it has to either go above the constant. Let's draw this value here. Let's dot it just for reference. Okay, this is the value at A and at B. So if the function is not constant, well, it's going to have to either go above this line or below this line, right? So let's assume it goes above this line. But it can't just go up and up and up and up and up, right? Why? Right, it has to get back, and we can't lift the pen off the board, right? So at some point, it's going to have to go down. Maybe it will do it more than once. Maybe it will go here down and then come back up again. It can do it 15 times. We don't know. But it's going to have, for example, a maximum point. Do you see that? And what do we know about the maximum point? By Fermat's theorem on the previous board, what do we know about this maximum point?
The derivative is 0.
Right. The derivative there is 0 by Fermat's theorem. In fact, so this is going to be this C that the theorem claims exists. Okay? And in this specific picture that I drew, there are actually two candidates, right? Two of them. Do you see? So do you agree again that this picture, okay, so here's the other one, that there are two C's here, so that this picture really reflects the statement of this theorem, and that it makes sense, right? It seems convincing. Does everybody agree?
Yeah.
Okay. So this is Roll's theorem. I forgot one thing I wanted to say about Fermat's theorem. Let's go back one step to this board. Do you know this theorem? I claim that you know this theorem. You've been using it, maybe without calling it Fermat's theorem, but you've been using it. When you studied functions and you want to explore them, to investigate a function, to graph it, usually the first thing that you do, well, maybe after finding the intercepts with the axes, what do? You find the derivative, set it equal to 0 to find maxima and minima, right? Does everybody know what I'm talking about? Okay, so that's what this theorem says. This is precisely this theorem. It says, if you're looking for maxima and minima, look for points where the derivative is 0. Because maximum and minimum points satisfy this. Do you agree? I kind of doubt that you encountered Roll's theorem, although it's also useful, but we are going to encounter it again. Okay? let's put on the third theorem for this sequence of theorems. If there are any questions whatsoever, please feel free to ask. Just raise your hand, and any question is good. Yes, but you just have to ask loud so I can hear. Excuse me? Yeah, this is short for such that. Okay? Yes?
When there's cusps, why can't there be maximum as well?
So the question is, why can't there be a maximum at a cusp? There can. Okay? But at cusps, the derivative is not defined. Okay? A cusp is a point where you can't say what the tangent line is. Okay? And this theorem doesn't hold. Okay? So Fermat's theorem doesn't say that those are the only points where maximum and minimum can occur. You know that. You know that they can occur, for example, at endpoints of the interval. Right? Fermat says, what are candidates for those points? Points where the derivative is 0. Okay? But there could be others. For example, cusps. For example, endpoints of the interval. Okay? The next theorem is named after another French mathematician called Lagrange. But this guy was actually born Italian, and his original name was Lagrangia. Anybody Italian to? Okay. But he eventually moved to France, and he was very famous by then, and he's buried at the Pantheon, and so nowadays he's considered as French. So this is a sequence of French theorems. Okay, and it says the following. So f is going to be like in Rolle's theorem. Let f be continuous on the closed interval and differentiable on the open interval, just like Rolle's theorem. But now I'm going to remove the assumption from Rolle's theorem that the values at the endpoints are the same. And the conclusion is going to be, then, there exists a C in the interval such that the derivative at C, I'm going to write something and then we're going to make a drawing to decipher it. The derivative is at C doesn't necessarily equal 0, but equals the value of f at A minus the value of f at B divided by the difference B minus A. And once again, let's draw this theorem. Let's get the intuition and see why this is really just as convincing as the previous ones. So what do I know? I know there's some interval here, AB. And I no longer have the assumptions that the values at the endpoints are the same. So I'm just going to draw some value at A. Here it is. And some value at B. Here it is. Now, let's again draw for reference this diagonal here. Now remember, when I'm going to draw the function, functions, by the way, are always blue. Okay? So, you know that, right? No, you have to, functions in blue. Please, all your functions have to be blue. Okay? Thank you. No, blue. Okay. You're going to have to get used to my sense of humor. You don't have a choice. You're stuck with me for the rest of the semester. Okay? Okay, so I know that I'm going to have to somehow get from here to here with no cusps and without lifting the pen off the board. Right? So one option is that the function is just a linear function. Right? In which case, what is the slope of this line? How do you find the slope of a line connecting two points? Right. It's the difference of the y values divided by the difference of the x values of the 2 points. Do you know that? So this point is the point b comma f of b, right? And this point is the point a comma f of a. Do you agree? And the difference of the y's divided by the difference of the x's is precisely this term we have here. Do you agree? So if the line is just, if the function is just a line, a linear function, then at any point, this is precisely the derivative. This is the slope, right? In the case where it's not, then it either goes above this line or it goes below this line, right? But it can't just go above and end up here, because it has to end up here, right? So if it somewhere goes above the line, it's going to have to come back, not necessarily come back down, but come back towards the line. Do you agree? Because it has to reach here. And if it at some point went below, it's going to have to come back up. Do you agree? Now there's a secret about this Lagrange à Lagrange guy. Okay? One second. He had a problem with his neck. Okay? So he was like this. Okay, good. Exactly like that. And he was a bright guy. He looked at Rolle's theorem. Remember Rolle's theorem? Here it is, right here. Take a quick peek at it. Okay? And he looked at Rolle's theorem, but he saw it like that. Okay, so look at this picture like that. What do you see? This is Rolle's theorem. It's just... Do you agree? So the statement is there's going to be a point here where the slope of the tangent line is not 0, but it's parallel to this line. And likewise in this picture here. So that's this statement. Do you agree? There is no evidence whatsoever that the nonsense I just said about Lagrange's neck is true. Okay, I just invented that. But clearly that's the intuition behind it, right? You can put your neck back up now. Oh, okay. Okay. Clear? Questions? Yes?
It doesn't have problems when the slope is not defined, when the first derivative is not defined?
No, but we're assuming all the goodness conditions here in the assumptions. We're assuming that the function is continuous and differentiable, which means that saying a function is differentiable is saying that the derivative exists at every point. So there's no problems with maybe points where the derivative is not defined or things like that. Once again, I don't want to get into the details of these theorems because I do want to do it, but later. Right now, it's just an introduction. It's just a really fast, intuitive line of theorems, and there's going to be a point to them at the end. Okay? So is Lagrange's theorem clear? What I want to show you is that Lagrange's theorem generalizes Rolle's theorem. Or another word to say it is that Rolle's theorem is a particular case, a special case of Lagrange's theorem. Why is that true? If you take, suppose we already know Lagrange's theorem. Okay, suppose we know this, suppose we proved this. If we take a function which happens to satisfy that the value at b equals the value at a, okay, if we take a function that satisfies that, what do we get here? If f of b equals f of a, what do we get here? 0. So if a function satisfies f of b equals f at a, we get Rolle's theorem. We get that there exists a point such that the derivative is 0. Do you see that? This is what it means to say that one theorem generalizes another theorem. Okay? Here's our next theorem, the fourth theorem in this sequence, named after a mathematician of which nationality? Wild guess.
Right.
Wild guess. Good! Good guess. His name was Cauchy, very famous. Very famous. Augustin Louis Cauchy. And his theorem deals with two functions. So let f and g be continuous on the closed interval and differentiable on the open interval. Assume, so here there is some more data. Assume that for any x in the interval AB, see, we're already starting to speak math, right? For any x in AB, the derivative of g at x is not 0. And now comes the then part. Then. So there are two assertions. The first one is very technical. Okay, it's not the one we're interested in. The first one says that g at A is not the same as g at B. This is very easy, by the way, to convince you, right? Because if g at A and g at B were the same, then there's going to have to be a point where the derivative is 0, right? But we're assuming that it's not. So g at A has to be different than g at B. And the second part, which is the one we're interested in, there exists, do you know this symbol? This symbol means there exists. It's like an upside down E. Okay? There exists a point C in the interval AB such that the derivative of f at the point C divided by the derivative of g at the point C equals f of b minus f of a divided by g at b minus g at a. Okay? So, I think the words are already clear at this point. I don't have to explain any new words. The first thing I want to show you is that this theorem, Cauchy's theorem, generalizes Lagrange's theorem. Okay? Let's see that. So, suppose we know Cauchy's theorem, apply it to a very specific function, to the function g of x equals x. Okay? Apply Cauchy's theorem to the function g of x equals x. You know that function, right? It's this function, right? What do you get in this formula? That's what I'm interested in. You get f prime at c divided by g prime at c, but remember, g is the function x. What's the derivative of x? 1. Does everybody know that? So here, you just get 1. Do you agree? So dividing by 1 is like doing nothing, right? So you get f prime c equals, and once again, g is the function x. So what is g of b? B. And what is g of a? A, right? So here you get b minus a. So do you see that applying this for a general f, but for g being specifically g of x equals x, we get precisely Lagrange's theorem on the previous board. Does everybody see that? So Lagrange's theorem is a special case of Cauchy's theorem. Okay? Question, yes?
Could you please repeat that?
Yes. What I said is that Lagrange's theorem is a special case of this. What does that mean? It means that if I restrict myself in this theorem somehow, I get Lagrange's theorem for free. Okay? And I told you how to do that restriction. Take G, which a priori is very general. All it needs to be is continuous and differentiable, right? Take G to be the specific function, g of x equals x. Plug it here, you get b. Plug it here, you get a. And plug the derivative at any point, you get 1. So you get Rolle's theorem, Lagrange's theorem for free. Okay? Okay. Now, there's a picture that goes along with Cauchy's theorem, but there's stuff you don't know in order to understand this picture completely. And I don't want at this point, it would be sidetracking to explain all that stuff. Okay, so what I'm going to do is just very, very, in a very, very quick and just draw the picture, and we will get to this stuff later. Okay? I'm not sure we will ever do this stuff in this course, because this is more related to Calculus 2 material. Okay? But I want you to, if you ever want to look at this and know what the intuition for this thing is, I want you to have that picture available. So, one way to give a function, or not even a function, a curve in general, so this is x and this is y as usual. But there are some curves in the world that are not graphs of functions. For example, a circle, right? A circle is not a graph of a function. Do you know that? Right? Because a function at every x has to have only one y value, right? So one way of giving the formula for a curve, which is not a graph of a function, is to give it as use two functions and a third variable called a parameter, and give the function in terms of a parameter. So x is going to be a function of t, and g is going to be a function of t, and t is the parameter. This is called a parametrization of a curve. Okay? So, and t is going to be taking values between a and b. Okay? So the curve is going to start when t equals a. When t equals a, I'm going to get the point, x is going to be g of a, y is going to be f of a. Okay? So I'm going to get the point here, xy, which is the point g of a, f of a. This is a bit small. Can you see this, or is it too small? Okay? So this point is for t equals a. The x is g of a, the y is f of a. And we're going to get another point for b. So this point is going to be the point where the y value is f of b, and the x value is g of b. Okay? And the curve itself is just going to somehow, remember, it's not a function anymore. Okay? So the curve itself is going to be something like this, maybe. Okay? Now, the slope of this line here is what? Is the difference of the y values, right? So it's f of b minus f of a divided by g of b minus g of a. Do you agree? So what this theorem says is that there's going to be a point somewhere. For example, here's one, and here's another one, and here's another one. Oh, there are many ones in this picture that I drew, where the slope of this curve is going to be precisely this value here. Okay? And what you need to know, the only thing you need to know, is that in order to find the slope of a parametric curve, the formula for it is precisely take the derivative of this and divide it by the derivative of this. Okay? So what this theorem says is that for a parametric curve like this, there's going to be a point where the slope is precisely this. Okay? If you didn't follow the details, this was really a crash course in the first, the first 3 lectures of Calculus 2, but don't worry about it. Okay? Don't worry about it. This is really just for intuition. You can see that it's kind of the same idea as the previous theorems, right? Right? Okay. So we have here 4 theorems: Fermat, Rolle, Lagrange, and Cauchy. And one is slightly more involved in general than the other. And I want to add one detail to this historic story that I just told you. And here's the missing details that will make this an interesting story, and in particular tell you why I've been babbling about this stuff as a first lecture in calculus. Okay? So what I want to add is the years in which these mathematicians lived. Okay? So Fermat was born in 1601. That's a long time ago. That's more than 400 years ago. And died in 1665. So this was an honest 17th century mathematician. Okay? So remember this. Rolle was born 1652 and died 1719. Okay? Lagrange was born 1736 and died 1813. And finally, Cauchy was born 1789 and died 1857, which is just slightly more than 150 years ago. So, if you look at all these dates, Fermat was born 1601, Cauchy died 1857. That's a 250-year gap. Do you see that? And, okay, so probably Fermat didn't invent this specific theorem the moment he opened his eyes, and probably Cauchy wrote this theorem a few years before he died, right? But still, it took mankind 200 years, give or take a few, to get from that theorem to this theorem. Do you see that? We just did it, not with full details, but we really kind of convinced. I mean, give me 10 more minutes and I could do this more precisely, but don't worry about that. We did it in what? Half an hour, right? I find that mind-boggling. How could it be that these 4 theorems, I mean, couldn't somebody before Lagrange do this with his neck and see Rolle's theorem and write that theorem? What's the big deal? Okay? And what I want to present is a possibility for an answer to that question. Okay? How come it took so long? And the facts of this answer are true. Okay? Saying that that's the reason why it took so long is arguable, but I think that is part of it, at least. And my theory is the following. Fermat really did first steps in calculus, really. And what he was working with, this guy was more of an amateur mathematician than a He did great, amazing things, but he started off playing with these things. And what he used, the tools he worked with, was really very good and bright intuitions. That's what he was working with. Okay? He tried to put in some formalism, and he did some stuff. He has some great, great advances in number theory and in various fields, but he was really working on intuitions. The next two folks here, Rolle and Lagrange, lived in a period where calculus was already being introduced as a very, very important topic, laying the foundations for very, very many fields. And these two people, Rolle and Lagrange, along with very famous other mathematicians like Isaac Newton, which you probably heard of. I mean, saying Isaac Newton is a mathematician is not very precise. I mean, that guy was a scientist. He did physics and astronomy and many, many, many things. And Gottfried Leibniz, a German mathematician. These people were already doing heavy calculus, but the tools they were using were somewhat weird, to say the least. They were using a notion, for all of this stuff, they were using a notion called an infinitesimal. Okay? Let me tell you what an infinitesimal is. An infinitesimal is a non-zero number, which in absolute value is smaller than any positive number. Again, a non-zero number, it can't be zero. Take its absolute value, it's smaller than any positive number. Can you give me an example of an infinitesimal? It doesn't really compile, right? 1/2 is not an infinitesimal, right? Because 1/2 is not smaller than any positive number. Do you agree? 0 is not an infinitesimal because we said an infinitesimal is not 0, right? So what is an infinitesimal? Yes?
1 times 10 to the negative infinity.
Okay, so one way to think of an infinitesimal is divide 1 by infinity. But what is that? What is infinity? How much is 1 over infinity? Is that a real number? Is that... Do you agree that there is a bit uneasiness when you speak of 1 over infinity or an infinitesimal? Okay? This is what these folks were working with. Newton and Leibniz and Lagrange and Rolle and many other mathematicians, they were working with infinitesimals. And they did amazing math, working with that bizarre notion. Okay? And then, only in the 19th century, came along Cauchy and invented the notion, the precise notion of a term called the limit. Okay? And it's not only Cauchy, it's work of, sometimes it's attributed to Karl Weierstrass, a German mathematician. It's not clear who invented the very precise definition, but they were working with it. Okay? They were working with the notion of the limit. And this precise notion of the limit, which we're going to discuss at great length later, and which we're going to see is the foundation for this entire course, derivatives are going to be defined via limits. Continuity is going to be defined via limits. Integrals are going to be defined by limits. Series are going to be defined by limits. Everything is going to be defined using this magic notion of a limit, which is not trivial, okay? And this notion is what enabled the breakthrough. Everything we're going to study in this course was already known. Not just these theorems. Everything we're going to say in this course was already known, I would guess by 1857, but maybe give or take 10 years. Okay, so in the 19th century, everything was already known. Okay, and not just this calculus, but also many other fields of mathematics, like complex function theory and many other fields, had an amazing breakthrough in this period of time because of that, I don't know, enlightening notion of the limit, okay? Which threw away into the abyss of history the notion of the infinitesimal and made precise the calculus that we're learning today, okay? So what I want to do is write for you the definition of a limit. It's going to look very, very scary. It's like nothing you've ever seen before, okay? But I just want you to get the flavor at this point. We're going to discuss it at length as we progress, okay? But just so you get the feeling, so you see what this... okay, we have to erase something, so let's start erasing. And by the way, let me remark that in the 20th century, the infinitesimals did make a certain comeback. So there's a field in mathematics called non-standard analysis, in which there was an attempt to make those infinitesimal things more precise and to make working with them rigorous and acceptable in today's standards. And it is due to a mathematician called Robinson. He did the main work in this topic. But as you can understand from the name, non-standard analysis, it's still in the outskirts of mathematics. So the mainstream mathematics that is done today uses this notion of the limit that I'm going to write now. So definition: the limit as x approaches a of f of x equals L. You've been working a bit with these things, right? You know how to calculate some of these, right? It's not the first time you're seeing this notion. Am I correct? Yeah. Okay. If for any epsilon greater than 0, this is the Greek letter E, there exists a delta greater than 0, this is the Greek letter D, such that if x minus a in absolute value is less than delta and greater than 0, this means that the distance from x to a is delta, then, or at most delta, then f of x minus L in absolute value is less than epsilon. Okay? Huh? Do you agree that the correct approach to this should be at this point? Huh? Okay, I agree. Don't worry about it. We're going to get to it. We're going to study it very carefully and understand what this means. Okay, and we're going to see how everything in this course, this gives rise to everything in this course, in calculus. Okay, but for now I just really want you to get a flavor of this thing, of this definition. And so this concludes our introduction, okay? But I want to add just a few more words. This is not an easy course, okay? One, we're going to be learning a new language, okay? In a couple weeks from now, I'm going to write this, and you're going to understand what it means. Hey, that's a new language, isn't it? Right? So that's one thing that makes it not easy. We're going to be learning mathematical thinking, mathematical logic, how to express yourself mathematically. That's something that you don't only take for this course or for Calculus 2. That's something that you take out there to the world. Okay? Rigorous mathematical thinking is very important to anybody that does science or engineering of any form. Okay? And on top of all that, we're going to be learning a lot of material. We're going to be mastering many, many techniques and I mean, you're going to learn how to take derivatives and how to calculate integrals and how to calculate limits and how to calculate series and lots of stuff. And we're not going to take 250 years to do it, only 3 months. Okay? So this is not an easy course. What I just said now says that it's legitimate to feel that it's hard. Okay? And it's legitimate to struggle, okay? I think everybody that takes this course struggles at some point or another. It's not an easy course. But, at the end, you want to pass, right? And you're going to pass if you do it right. And doing it right means doing your homework. It's not a spectator sport, okay? You can't just look at me, even if you understand everything I say, you're not going to be able to do it on your own. You have to get your hands dirty. Okay? Do a lot of practice. Work hard. Ask many, many questions. Whenever something is not clear, ask. Okay? And it's going to be okay. And my hope is that it's also going to be a bit of fun. I know this is wishful thinking, but maybe. Okay? So let's have a 10-minute break now.